Hey everyone, welcome back. In this video, we're going to talk about the divergence theorem, which gives us kind of an interesting relationship between the change in a vector field over a particular volume and its flux through a particular surface. So let's go ahead and take a look at that. So in particular, what the divergence theorem says is that if we have a triple integral so we've got this kind of like gradient operator dotted with our vector field, which really is just kind of a notion of how much our vector field is changing at a point. And then integrate that over a volume. Then this is equal to a double integral over the boundary of the surface or the volume that we're looking at, f dot ds. So we've basically taken a volume integral and figured out how to turn it into a surface integral, kind of notching it down an entire dimension, which is really kind of interesting. But if we think about this physically, it makes sense. And really what this is saying is that this is how much it's spreading out. So think about this as being something that's spreading out over a volume. Well, that has to be equal to the flux that's going out through the boundary. And what does that mean? Okay, so again, maybe that's just a lot of words that are kind of floating around. An intuition behind it that I like to think about is that imagine you have a sponge and it's full of water, okay? So this sponge is your volume, okay? But you also know that your sponge, it's got kind of like, it's got its faces, its edges and stuff like that. And what we can think about is the motion of the water inside of your sponge. So you have your vector field, which is the motion of the water inside of the sponge, which is your volume. If we change the motion of the water, like how that water is shaped in there by squeezing the sponge, which is this guy right here, then the amount of water that leaves the sponge, so how much is changing the amount of water inside of the sponge, has to be equal to the amount of water that passes, well, out of the sponge, right? So we have this idea of we're changing the amount of water, we're changing the shape of the water and changing how it moves. Well, the amount that it moves around and the amount that leaves is ultimately, it has to pass through the edges of the sponge. So that's kind of one way to think about how they're related there. So now each of these, we know how to compute volume integrals, and we actually talked in our last video about how to compute surface integrals. So we're going to go ahead and work a couple of examples where we just compute this type of integral both ways. We're going to do both the volume integral and the surface integral to be able to check to make sure that the divergence theorem does indeed actually work out. And one thing that I do want to note is that we assume here, when we're working with our surface integrals, we assume that this has a outward orientation. Okay, so it's just something that it won't, if you get into these kinds of problems, it won't specify, okay, assume that your surface has an inward or an outward orientation. You should just know that when you're working with the divergence theorem, you're going to want to look for your surface to have an outward orientation. So let's go ahead and get started. All right, so in our first example, we are going to let omega be equal to x, y, z, and x squared plus y squared plus z squared less than or equal to 4, and z greater than or equal to 0. And our vector field is going to be f of x, y, z equal to x, z, y. And like I said earlier, we will check that the triple integral over our surface of this gradient operator dotted with f dv is indeed equal to the double integral over the boundary. I guess I drew that wrong earlier. I put a little delta there. This should really be a partial. It means boundary. So the boundary of omega f dot ds. Okay, so the first thing I'm going to do is going to be this guy right here, and then we will compute this one. So All right, so we're looking at, actually, maybe I'll just use some color for these. So we're going to first check this one. Triple integral over omega gradient operator dotted with f dv. So for this one right here, we want to take this gradient dot f. So if you don't remember what that is, we're just taking these partial derivative vectors or operators. We're not really taking the partial derivative yet or anything. And we dot that with f. So this is going to be equal to partial with respect to x of x, which is 1, partial with respect to y of z, which is 0, partial with respect to z of y, which is equal to 0. So that's just equal to 1. So this triple integral that we're looking at right here is now going to become triple integral over omega of 1 dv. And if we kind of remember back, whenever we have a triple integral over, a volume, we're really just going to wind up getting the volume of our region. And in this particular case, if we look back up here, this is really just a half sphere because we're looking at, well, this guy right here is a sphere with radius 2. And we're telling ourselves that we want z to be greater than or equal to 0. So this is the volume of half sphere of radius 2, which just kind of reaching back to some high school geometry, we're ultimately going to get 16 pi over 3 as being the volume for that. So computing the volume integral, at least in this case, really wasn't all that bad. So let's go ahead and look at our boundary option now, the second half of our divergence theorem. So again, the little partial in front of a region means that you're looking at only the boundary or the outside of it. So we have f dot ds. And just kind of remembering back to our previous video, this is equal to the double integral over d of f r of uv dotted with n du dv. So where that r of uv is a parameterization for our surface. Now, one thing that I want to emphasize is that this guy right here is, since that's our boundary of, it's a shape that looks kind of like, well, it's a half sphere, so it looks like this. And we really just want the shell. We don't want the inside of it. We just want the outside of it, okay? So it's really just kind of, we're not filling it in. It's just the part where we have equality, not less than or anything like that. So boundary equals outer shell. And in this particular instance, our boundary is, well, it's that hemisphere on top, but we're also including the disk at the bottom, since we have x squared plus y squared plus z squared equals 4. This is our upper hemisphere. And then we also have the z equal to 0 part, which is what gives us that disk right there. So we need to break our integral into 2 parts. Okay, so let's go ahead and do that. We can start with the disk on the bottom. That's really kind of the easy one. So when we're looking at this guy right here, something that we kind of want to keep in mind about this piece is that it's actually just something that's normal to our surface. It's not, I mean, like, we've got that equation that we can use to compute it, but when we're looking at something like a disk where it's flat along the XY plane, we can actually kind of just look at it and be like, okay, this is what our normal vector is. And we're going to observe that any vector that's perpendicular to that disk there that's lying flat on the XY plane has to be of the form, well, we can take 0, 0, -1, basically. We want it to point downward because we need our outward orientation. So like so. But yeah, so it's only going to have a z component because we want it to just point either straight up or straight down. And because we need the outward orientation in order to do the divergence theorem, we're going to take the negative version of that. So if I dot this with n or with f, what I'm going to get is just going to be negative y is what I get out of that. So really the only piece that I have to worry about translating over is going to be, well, it's just going to be the y component there. So, but if we wanted to parameterize our disk, since it really is just a disk, we can kind of treat it like it's a circle, and we're going to get r u v equal to u cosine of v, u sine of v, and we have 0 in the z component since it's flat in the xy plane. And our radius u is going from 0 to 2. And we want v to go all the way around, or we want our shape to go all the way around, so we need v to be able to be between 0 and 2 pi. So these are going to be our bounds of integration, and we note that this also implies that f dot n is equal to just a negative u sine of v. Now, if I'd wanted to, I could have parameterized it first and then plugged them into f and then taken my dot product, but I mean, that winds up being a little bit time consuming, and we can save a lot of time in this particular case by taking the dot product first and then making the substitutions necessary. Okay, so I think we are actually ready to go ahead and start plugging things in. We have our integral from 0 to 2 pi. This is using this equation right here. Integral from 0 to 2 pi, integral from 0 to 2. We already computed f dot n and found that to be negative u sine of v du dv. And this is really just equal to integral from 0 to 2 pi. I'm actually going to go ahead and swap my order of integration here. So I have 0 to 2, integral from 0 to 2 pi, which I can do freely since my bounds are dependent on each other. Negative u sine of v dv du. And the reason that I do this is because I note that integral from 0 to 2, u, I guess I have that negative in there, integral from 0 to 2 pi, sine of v dv du, well, this is actually just going to be equal to 0, since what this guy right here winds up being is cosine of 2 pi minus cosine of 0, which is just equal to 1 minus 1, which is just 0. So, and this is actually going to be something that we're going to use a few times, is the fact that anytime we take an integral over sine from 0 to 2 pi, I'm just going to get 0 out of it. So be on the lookout for that as we go through our next couple of integrals here. But that simplifies the process down quite a bit there. I just get 0 from my disk. It contributes absolutely nothing to the flux that's going through our surface here. Okay. So now we got to work with this upper hemisphere thing. Okay, so the first thing we're going to want to do is parameterize it, because the normal for it isn't quite as nice as it is in the other one. So we are actually going to want to walk through all of the steps for that. Since we are looking at a sphere, we're going to want to use spherical coordinates, and parameterizing with spherical coordinates really just means that we're taking our spherical identities and plugging them into the x, y, and z components. So we get r of uv is equal to 2 sine v cosine of u, 2 sine v sine of u, and 2 cosine of v. Okay. And since, I guess I can go back and look at our picture again here, since we do want to make sure that we're taking the entire hemisphere all the way around, at least around the xy plane anyway, and we only want the top half of it though, we want our u to be able to go all the way around, so 0 to 2 pi, and I want v to be between 0 and pi over 2. Okay, So, all right, let's go ahead. And I think in this one, I'm actually going to work through the details of finding RU, RV, and R normal vector. So we have RU, which is equal to I'm going to get 2 sine V. Oh, that should be a negative 2 sine V cosine sine of U. 2 sine of V cosine of U, and then 0. And then R of V is equal to negative 2 cosine of V that should be a positive 2 cosine V cosine U 2 cosine V sine of U, and then negative 2 sine of V. Okay, so taking RU cross RV, see if this even fits here. Okay, so we've got negative 2 sine of V sine of U, 2 sine V cosine U, 0, and then I've got 2 cosine of V cosine of U, 2 cosine V sine U, and negative 2 sine V. Okay, just about. Now taking this cross product here, what we wind up with is I hat times, we're going to get negative 4 sine squared V cosine of U minus J hat times, looks like 4 sine squared V sine of U, and then plus K hat times negative 4 sine V cosine V sine squared U minus 4 sine V cosine V, and then cosine squared U. From here, we're going to get negative 4 sine squared V cosine U, negative 4 sine squared V sine of U. And then thankfully, this is going to simplify down quite a bit because we got that sine squared cosine squared thing going on there. And we're going to get negative 4 sine of V cosine of V. Okay. Great. Yeah, okay, so that is going to be our normal vector. So now I want to make sure, and this is, again, going back to kind of like in our previous video, we talked about making sure that our orientation on this guy is correct. So we want our normal vectors to be pointing outward, okay? So our goal is to get them pointing up, out, like so. However, we noticed that if we were to plug in, say, I don't know, like pi over 4 into each of these, which would land us kind of here in our first quadrant here. Each of these terms is going to be negative, which means that what I'm ultimately going to wind up with then is going to be something that points inward. And I don't want it to point inward. I want it to point outward. So to fix that, I'm going to multiply by negative 1. So yeah, it's not a big deal if the orientation winds up backwards. Sometimes that happens, sometimes it doesn't. And all you got to do to fix it is just multiply by negative 1 to turn those vectors around. So, okay. Great. Okay, so I think we are just about ready to set up our integral. So I think we get, let's see here. We're going to have the integral from 0 to pi over 2, integral from 0 to 2 pi. And then we have our remember we're shooting for, we need this guy right here, our vector field evaluated at r of uv, which is going to give me 2 cosine of u sine of v, 2 cosine v, 2 sine of u sine of v. And then we're dotting that with our normal vector that we're going to multiply by -1 to correct the orientation. So we're going to have 4 sine squared v cosine u, 4 sine squared v sine of u, and 4 sine v cosine of v. And then there's a du dv here as well. Okay, so let's go ahead and compute this integral. This is equal to the integral from 0 to pi over 2, integral from 0 to 2 pi. Okay, so I guess the first thing to do is going to be to compute that dot product that we had. So I've got that it is, we get 8 cosine squared u sine cubed v plus 8 sine of u cosine of v sine squared v, and then plus 8 sine of u cosine v sine squared v, and then du dv. Okay, so that's quite a bit, but we are going to find that that all simplifies down quite a lot, because we notice, first of all, these two terms here are the same. So, I mean, the first thing that we can do here is, and I'm actually going to go ahead and split the integral when I do this, and you'll see why in just a second. Integral from pi over 2, integral 0 to 2 pi, 8 cosine squared u sine cubed v du dv, and then plus the integral from 0 to pi over 2, integral from 0 to 2 pi of 16 sine of u cosine v sine squared v du dv. So now the first thing that I'm going to do here is we note that this guy right here, this is equal to the integral from 0 to pi over 2. And I can factor all the stuff that has to do with v to the outside, and also I guess that's 16. Cosine v sine squared v. And then we have the integral from 0 to 2 pi of sine of u du dv. Now, remember back to, well, just a second ago, that this piece right here is 0. So this whole integral, this whole extra term here is equal to 0. So really the only piece that we have to deal with is going to be this guy up here. So that actually simplifies things down quite a lot. So this is equal to 8 times the integral from 0 to pi over 2, integral from 0 to 2 pi, cosine squared u sine cubed v du dv. Okay, so I guess I need to integrate with respect to u first. So 8 integral from 0 to pi over 2. I'm going to go ahead and pull that sine cubed v out to the front. And then we have our integral from 0 to 2 pi. I'm going to use a power reduction formula on this. It's going to be 1/2 times 1 plus cosine of 2u du dv, and that is equal to 8 integral from 0 to pi over 2 sine cubed v, and then I have u over 2 plus 1/4 of sine 2u evaluated from 0 to 2 pi dv. And this guy right here is just going to be 0 for both of those because you plug either of these two into it and you're going to get 0. So I'm going to get 8 times, looks like pi over 2. Oop, not pi over 2, 2 pi over 2, which is just pi, integral from 0 to pi over 2, and then sine cubed v dv. And to get this part right here, we do sine times 1 minus cosine squared v dv. And I'm going to use a u sub. And I guess, I mean, we've already used the letter u though, so I guess we'll use the letter w equal to cosine of v. So then dw is equal to negative sine v dv. And I've got that right here, although I guess I need to swap my negative around like so. Okay. So this is equal to 8 pi, and I'm going to drop my bounds here for a second. I'll put them back when it comes time later. But negative 1 minus w squared dw equal to 8 pi negative w plus 1/3 w squared. And then at this point, I'm going to go ahead and plug back in my cosine of v, so that way I'm not worried with what my bounds have to be and stuff. Cosine v plus 1/3 cosine cubed v, and this evaluated from 0 to pi over 2, which is ultimately just going to give me 16 pi over 3. And remembering back that with our other option for how to compute this, this was the value that we got. So it does indeed match, and we did confirm the divergence theorem, at least in this case. So yeah, so I guess that was quite a lot of work. But yeah, so it's just the point of this is just that there's a couple of different ways to think about working with integrals. So one of them is you can work with the whole volume, or we can work with just like the surface on the volume instead. Let's do one more example. Okay, so in this one, we have that our volume is equal to x, y, z, such that z is less than or equal to 36 minus x squared plus y squared, and then z greater than or equal to 0. So, and then our vector field is going to look like, we've got 1, 2z, and then 3 plus 4z. Okay, so I guess first things, I'm going to go ahead and sketch and see what this region looks like. It's really just an upside down paraboloid. I can tell that it's a paraboloid from this x squared, y squared, and having the z thing going on here. And I know that it's upside down because of the negative, and then I know that it's been raised 36 units. So it's going to look something kind of like this. Okay, this is a paraboloid, not a lopsided sphere. I feel like I should clarify that. Okay. So, all right, let's go ahead and work with our first one, which last time was just we're doing the triple integral over omega for gradient operator dotted with f dv first. So before we can integrate over this surface, we need to write it into a coordinate system that makes a lot more sense to work with. And this particular instance is going to be cylindrical coordinates because we have these x squared, y squareds here, and then the z's are isolated. So ultimately, we're going to have omega equal to r, theta, and z, such that z is less than or equal to 36 minus r squared. The r squared just replaces the x squared, y squared. We know that z is greater than or equal to 0. We also know from this right here that 36 minus r squared has to be greater than or equal to 0. It comes from both of these two pieces here, which means that r has to be less than or equal to 6. So 0 less than or equal to r less than or equal to 6. And then finally, because we're going all the way around the circle, we need theta to be between 0 and 2 pi. So those are going to become our bounds of integration. So our vector field is just 1, 2, z, 3 plus 4z. And so that means that when I take my gradient operator and multiply it by f, or dot it with f, I guess, excuse me, I'm just going to get 0. This is going to be plus 0 and then plus 4. Yeah, so that's pretty much all there is to that piece right there. And I'm ready to plug everything into my triple integral here. So triple integral gradient dot f, or not the gradient, I shouldn't say the gradient operator type thing, dotted with f, dv is equal to the integral from 0 to 2 pi, integral from 0 to 6, integral from 0 to 36 minus r squared. Notice that this one has to be on the inside because it's dependent on other variables. And then we have 4, and then we have r from swapping over to cylindrical coordinates, and then we have dz, dr, d theta. Again, dz has to come before dr because the bounds of integration for z are dependent on r. So yeah, if you go through and compute this integral, it winds up being quite straightforward to do, a lot simpler than our previous one. So I'm going to leave that little bit to you. What you ultimately get out of that is going to be 2,592. So yeah, so that's one method to do it. Really quite straightforward there. So let's check to see if we use our other option with the divergence theorem, if we get the same number. Okay, so now we're looking at double integral over the boundary of our region, f dot ds, which we can use our equation from a surface integral from earlier. So we have our double integral over f r u v dotted with n, and then du dv. Okay. So in this particular instance, our boundary here was this paraboloid thing going on with the disk down at the bottom. Okay, so that means that we're going to need 2 pieces for our integral. Oh, I misspelled the word 2. Oh my goodness. 2 pieces. Okay, so let's go ahead and start with our disk because that's kind of the easier one of the 2 to work with. So for the disk, we said earlier that it has a normal equal to 0, 0, negative 1. And the parameterization for the disk was just r of u v equal to u cosine v, u sine of v, and then 0. Okay, so because I mean it's the same idea, same shaped disk, maybe just a different size because the radius will be a little bit different, but same idea as from earlier. If I take f dotted with n, we're going to get this is just going to be equal to 1, 0, and then 3. And the reason for that are dotted with 0, 0, negative 1. So this guy right here arises because z is equal to 0. So then what we're going to get is 1 and then 2 times 0 and then 3 plus 0. So just so you're aware of where this piece here came from. So yeah, so you take that dot product and you're going to get negative 3. So actually this one works out quite nicely because what you then get is a double integral over the disk of negative 3 and then really just kind of a dA there, which is equal to negative 3 times the area of the disk. And well, the area of a disk is just the radius of the disk squared, which is 6 pi. So we're going to get negative 108 pi as being the flux that is contributed by the disk at the bottom. So, okay, so that wasn't too bad. We still have to compute the second piece. So for our paraboloid, which I will denote paraboloid, which I'll denote P, we will also parameterize this with cylindrical coordinates. So a lot of times, the parameterization that you used for the volume will wind up being basically the same as the parameterization that you use for your surface. You just have to figure out how to plug it into or not a parameterization, but the coordinate system you use for the volume will be the same as the coordinate system that you use for your parameterization. So the only difference then winds up being that when you're working with the surface, you have to do this parameterization with the R and the U and the V, whereas earlier with the volume, you could just work with all the pieces individually and not worry about trying to squish them into a vector. So, but anyway, we parameterize with the cylindrical coordinates. Which means that R of U V is equal to U cosine of V, U sine of V, and then our Z component is that 36 minus U squared. And same as from earlier, we know that U has to be between 0 and 6, and V has to be between 0 and 2 pi. Okay, so this means that my vector field now becomes 1, 2 times 36 minus U squared, and then 3 plus 4, 36 minus U squared. So R U equal to cosine V, and this is so we can compute our normal vector, and cosine of V, sine of V, negative 2U, and then our V is equal to negative U sine of V, U cosine of V 0. So pretty straightforward computation to get the cross product of those two. So I'm just going to give it to you. N is equal to 2U squared cosine of V, 2U squared sine V, and then U. So we now have our normal vector, and it is time to ask ourselves, do we need to turn it around? So we look at our surface here, and our goal is, because of the divergence theorem, we need our vector to be pointing in an outward direction, like so. Okay, and we kind of already did that for our base by making it negative. So we need to determine whether or not our vector is pointing upward. So if we look at this, if I plug in some positive u, say 1, for example, then I know that because this z component here is positive, that my vector is pointing upward. I really don't even have to mess with what these guys look like. U being positive means the vector points upward, which means that I am indeed pointing out and away from my surface. So I am good to go. Great. Okay, so now we're ready to start plugging some things in. We are going to get, we're integrating over our paraboloid. This will be equal to the double integral 0 to 6 integral from 0 to 2 pi of 1, 2, 36 minus u squared, 3 plus 4, 36 minus u squared, dotted with 2u squared cosine v, 2u squared sine of v, u du dv. Okay, that is a u there, I promise. U. Oops, can't even see that. Okay, du dv. So, well, I guess I can take the dot product. Integral from 0 to 6, integral from 0 to 2 pi. I'm going to get 2u squared cosine v plus 4 times 36 minus u squared sine v. And then there should be a du dv. Oh, actually, I don't need that yet. I'm not going to break it up yet. I'll break it up in a second. And then plus, looks like I'll get 3u plus 4u 36 minus u squared. And then du dv. Now, I'm going to apply the same trick that we did earlier with our sine. And actually, it applies to cosine as well. So I'm going to go ahead and split this up. I'm going to get integral from 0 to 6, 2u squared, integral from 0 to 2 pi, cosine v d du, and then plus, let's see here, integral from 0 to 6, 4 times, I'll put that on the next line, integral from 0 to 6, 4 times 36 minus u squared, and then u squared, integral from 0 to 2 pi sine of v dv du, and then plus integral from 0 to 6, integral from 0 to 2 pi of 3u plus 4u 36 minus u squared du. Oops. I lied earlier. I was so emphatic about it. I apologize. So dv du. Oh my goodness. Dv du, or is that order of integration there? Okay. So again, same trick as from earlier. This guy right here, 0. So that knocks out this entire term. Also, similarly, this piece right here, I've got sine of 2 pi minus sine of 0. Well, that's just equal to 0. So this whole piece, gone. The only piece that we have to worry about now is just going to be that last term right there. So let me grab a new page. And I will write that down again, so that way we have a nice clean copy of it. So we have the integral from 0 to 6, integral from 0 to 2 pi, 3u plus 4u 36 minus u squared dv du. So, and actually, now at this point, it's quite simple to calculate. You just use, I guess, standard integrating methods, no fancy tricks or anything like that. You're going to get 2,700 times pi out of that. So this is the piece from the paraboloid. And we had from earlier that we got a negative 108 pi from our disk at the bottom. So we have to add our two pieces together. And we have double integral over the boundary. F dot ds is in total negative 108 pi plus 2,700 pi, which is equal to that value of 2,592 pi that we got earlier, just simply, well, computing the volume of our paraboloid. So, yeah. Anyway, that's kind of it. That's the idea. I mean, I guess this is a lot longer and more tedious and a little bit messier than the first method that we looked at for the divergence theorem. But anyway, the point is that you can flip-flop back and forth between these two methods for computing integrals. And you wind up with the same value because, again, the amount that you spread out in your volume has to be equal to, well, the amount that's passing through the boundary. So again, kind of that visualization of the amount of water that was inside of that sponge and how it's moving has to somehow be equal or, related to how much actually winds up leaving the sponge when you squeeze it. So yeah, okay, so that's pretty much it. I'll see you guys next time.